Chapter 5, Water for Life, Part 2. We're going to look at aqueous solutions, meaning solutions where water is the solvent, and then we'll look at solutes. Please watch the following videos as an overview of aqueous solutions and the concept of molarity. So, a solution is a homogeneous mixture of uniform composition. That means if you take a part of a solution, any part, it should look the same as any other part. Solutions are made up of solvents and solutes. A solvent is essentially what is dissolving the other substance, and it's usually present in greater amounts. The solute is what we dissolve in the solvent, and that's usually present as the lesser amount. When water is the solvent, it's called an aqueous solution. Let's take a look at preparing a solution in concentrations. So here we have a little applet that we can use to examine concentration. Over here on the right, there's a color gradient that shows when it's the most red versus a light red, the concentration of the solution is very high. Over here on the left, we have moles of solute. At the bottom, there's none. At the top, there's lots. Then we have the total solution volume. At the bottom, there's low, and at the top, it's full. So let's start with a simple drink mix and go all the way down to 0 amount of solute. Now, if we add more solute, it starts to become more and more concentrated. And if we were to maximize the amount of solute for this particular example, it would be in the middle in terms of concentration. Now, if we lowered our volume of solvent, or the total solution volume, it would get more and more concentrated as we removed more and more of the solvent. Or if we increase the amount of solvent, it would get more and more dilute. This was just for a drink mix. Let's try gold chloride instead of a drink mix now. So first we start adding some gold chloride. Our concentration increases, it increases, and then all of a sudden the solution becomes saturated. And instead of the gold chloride dissolving, it just kind of sits at the bottom as a solid. Something very similar happens if you try to put sugar into iced tea. Sugar is soluble in cold water up to a certain point, but then if you continue to add sugar, the solution becomes saturated. There are a number of ways we can express the concentration of a solution. One is mass percent. That's grams of solute per grams of solution. And when we talk about grams of solution, the solution is composed of both the solute and the solvent. For example, if we were to take 20 grams of sodium chloride and put it into 80 grams of water, our solute concentration would be divided by the total solution mass. So 20 grams of sodium chloride in a total of 100 grams of solution. Multiply by 100 to get percent. And frequently we put this little mm notation to indicate this is a mass percent. Parts per million is another concentration term frequently found on your municipal water disclosure forms regarding pollutants or the addition of chlorine gas, which we'll talk later on about. So parts per million, one way to interpret it is milligrams of solute in liters of solvent. So if you have 0.50 grams of sodium chloride in 450 milliliters of water, you would take the 0.50 grams of sodium chloride, convert it to milligrams, using our unit analysis, units of grams cancel, and then you can stop there and then just divide by liters. The way I set it up here is I set it up using the unit analysis. So I took the inverse of the volume, essentially dividing by the volume. But remember, we need it in liters, so we do need to convert that into liters. And once you do the math, you come up with 5 times 10 to the 5th parts per million. Parts per billion is, instead of milligrams, it's micrograms per liter. So if they tell you you have a 2 part per billion solution, you have 1 liter of a 2 parts per billion, how many moles do we have? The way we'd set this up is 2 parts per billion is the same as saying 2 micrograms per liter. We have 1 liter of solution, so liters cancel. We need to convert micrograms to grams in order to use our molar mass to get moles. Here we have the molar mass of lead. And our units cancel nicely to give us moles. So 2 parts per billion is a very small number of moles of lead. Molarity is moles of solute over liters of solution. Usually brackets are used to denote concentration. When you put a bracket around a molecule, it's referring to the concentration of that molecule in units of molarity. For example, if I were to do something like this, NaCl be the concentration of sodium chloride in liters of solution, usually water. So here we have a 1 molar sodium chloride solution. That's 1 mole of sodium chloride per liter of solution. Also, this solution has a concentration of 1 moles per liter of the sodium ion and 1 mole per liter of the chloride anion. And we'll talk a little bit later on about how this ionic compound dissociates in solution. The reason why you have 1 of each ion, it's like saying, okay, I have a mole of bicycles. How many tires, how many front tires do I have? Well, I'd have 1 mole of front tires. How many rear tires would I have? I would have 1 mole of rear tires. So if sodium is our front tire and chlorine is our rear tire, we'd have 1 mole of each as well. Just a little overview on preparing solutions. The key idea here is that whenever you prepare a solution to a set volume of water, frequently we use these very precise volumetric flasks in the lab. What you do is you add your solute in a little bit of water and mix it well. Then you add water up to the designated total volume mark. You don't want to add the sodium chloride to a full liter of water. The reason being is that sodium chloride takes up volume. So you're going to end up having more than a liter of solution. So you add the sodium chloride or whatever you're working with, dissolve it up, then fill to the total volume of solution that you're looking for. Example problem. What is the concentration in molarity and mass percent of the resulting solution when you add 5 grams of sodium hydroxide to a 100 milliliter flask and fill up to the 100 milliliter mark with water? So assume you have 100 total grams of solution, since water is 1 gram per milliliter, and we're just going to assume, even though it's a sodium hydroxide solution in water, it's going to have roughly the same density of water. So we have 5 grams of sodium hydroxide in 100 grams of solution. It's just a 5% sodium hydroxide solution. Now, to get molarity, we need the number of moles of sodium hydroxide. So we need to use the molar mass, multiply by the molar mass, to get moles of sodium hydroxide. Then divide that by the number of liters, in this case 0.10 liters. And we would end up then with a 1.25 molar solution of NaOH. the number of moles per liter. When we divide through by whatever liters were given, the ending result will be per liter. Thinker Buddy, what is the molarity of a solution containing 3.5 moles of HCl in 5 liters of solution? Well, we simply divide the number of moles by the number of liters to get moles per liter. So the answer is 0.70 molar units. Let's watch a video on solubility. There's also an optional accessible article describing the phenomenon. This brings us to the concept of electrolytes. You've heard about electrolytes perhaps in Gatorade, or whenever you're doing something very physical, you need to keep your level of electrolytes up. The reason being is these ions in your body are important in relaying electrical signals within your body and brain. So there's different classes of electrolytes. There's non-conducting or non-electrolyte, like sugar, which doesn't conduct any electricity in water. And pure water actually is non-conducting as well. Then why be worried about standing in a puddle of water in your basement and working on your fuse box if water is non-conducting? Well, the reason is there are minerals and potentially metal ions that the water has collected when it seeps through the earth or is collected in the reservoir or goes through metal pipes. And those ions in the water are what help it to conduct electricity. It's not the water itself, it's any ions dissolved in the water. Something like any ionic compound that dissolves in water will conduct electricity and is an electrolyte. Let's explore ionic bonding. So ionic bonds are formed by a transfer of electrons. This is one way of showing it using Lewis dot structures, and we put these brackets around the ion. Notice how we show the ions next to one another, and the X is just to help you distinguish where the electron came from, in that it came from the sodium ion or atom. So these are very strong electrostatic attraction between positively charged particles and negatively charged particles. These are different than the partial charges we were looking at in between molecules. These charges are much larger. These would be referred to perhaps as full negative or full positive charges. When you have a crystal of salt, you have the sodium and the chlorine ions all stacked on top of one another in this huge lattice structure. We'll explore the concept of ionic bonds a little more in part 3, but this ends the second part of chapter 5.